Okay. This is one of my favorites because it's one of my fields, really, is optical communications. Here's an overview. I'm not saying we'll spend very much time at all on most of these topics. You see there's quite a few here. And some of these that we don't cover in as much detail might be good choices for a term paper. Telecom has so much information in it, so I just kind of hit on the key elements as I see them. And then anything you want to learn more about, that would be a good topic for the term paper. How many people have heard FTTX? FTTX. FTTX. Fiber to the whatever, right? And so there's FTTH would be fiber to the home, fiber to the curb, fiber to the building, fiber to the tower. So there is a FT cubed would be fiber to the radio tower, right? The explosion in wireless, the need for wireless bandwidth is helping the optical community because it's going to have to go over fiber at some point, right? So how are you going to handle all that? Well, you can design smarter and smarter networks, and we'll go through some of that. All right, there's some tricks that can be used in making your networks just work better and more efficiently and all that. But that alone is not going to keep up with the exponential increase in the need for bandwidth. And by bandwidth here I mean capacity, the ability, the data rate, the ability to send huge amounts of data at highest speeds possible. So it's really at the physical layer where things happen and that are going to keep us going. So I put a lot of that in here as well. So there's going to be next generation systems. I want you to not only understand what's out there now, but also understand the fundamentals well enough to where when the next stuff comes along, you'll be able to assess it properly and say, well, yes, that makes sense, or no, that's, you're giving me a sales pitch here that doesn't have any grounds to stand on. So you can read as well as I can, and probably better. Another hot topic here, so there's new stuff in photonic crystal fiber, for example. Optical fiber amplifiers are all over the place. We'd really like to have all optical signal processing, which we don't have much of yet. And there are no prerequisites. We focus on high-tech. Is that? I guess that's, I'm going to have to turn the table somehow. The table and the camera don't line up. I like to focus on high-tech but minimal math, right? I only use as much math as I need to make the point. Okay, so if you know how to multiply and divide, that's enough math. You might have to count, right? For example, remember those of you who've seen me do it before, you know, how many bits does it take to point at one of 8 things? Well, we counted it out, right? And we just counted in binary and showed how, oh, okay, so that turns into 2 to the 3, which is also known as 8. So there are 3 bits. If I send you one of 8 things, I'm sending you 3 bits of information. Right? If I only have 2 cats, Betty and Fred, and I put them in a bag and I mail it to you, and you open it up and you go, oh, it's Fred. Well, I just told you one of 2 things, right? That's 1 bit, one of 2 things. Right? So we do it in a way where anybody should be able to fathom this wonderful stuff. So this is not a timeline, but this is just kind of a list of topics here. We will cover the various impairments and ways to get around them. That's what mitigation means. Mitigate it, reduce the impact. State-of-the-art technologies and networks, and the next generation stuff. So, for example, let's just mention briefly that in optical fiber, and fiber, of course, is one of the biggest mediums, physical mediums for optical communications. There is free space optical, right? And I try to work in some marketing things as well for those of a more business orientation. And it's really, telecom's an interesting combination of business, regulation, policy, and the technology. So try to mix in all those things every now and then. Say I'm in New York City and I've got an office here and an office in the building right across the street. And we're even doing some cloud stuff. So I have huge amounts of data I need to transfer back and forth. Should I install fiber between the two buildings? The cost would be huge because permission to run something in the ground in New York City is going to cost quite a bit. If you have to dig your own hole, forget it in New York, right? But even just getting permission to run something through the hole that's already in there, the tunnel, could be prohibitive. So maybe you go free space optical, which is LED on the cheap side, a laser diode if you want it cleaner, and a photodetector on the other side. Maybe you have lenses, and it works just like wireless, except the frequency of the carrier is very high optical frequency instead of being at 1.4 gigahertz or something like Wi-Fi, which is in the microwave. So anyway, a lot of this stuff is over fiber, and if you look at loss as an important parameter versus wavelength, and there's materials absorb at different colors better than others, right? So standard fiber might have a transmission window that looks like that. And this might be around the infrared, typically 1550 nanometers. I'll cover, there aren't too many units to be covered here. Wavelengths is a length, so it's in meters, and nano means 10 to the minus 9. 10 to the minus 9 meters, so that's pretty tiny. But it's still infrared. I can't see it. I go to shorter wavelengths. I'm going from the red, it's kind of the red side, or the longer wavelengths, and blue is shorter wavelengths, just like would be true in the rainbow. Right? And, so you've got this narrow band of frequencies over which you have low loss, and that's where your telecommunication systems operate. So this is maybe regular fiber. This is existing or state-of-the-art. But then it's because fiber is mainly glass, and glass, like any other material, absorbs things, and it absorbs different colors. This one doesn't absorb purple so well, so that's why you're seeing it. His is not absorbing green so well, so that's why his looks green, etc. So you got this absorption curve. But if I'm in empty space, there's nothing to absorb, right? And air is pretty close to free space. Not as good as, on the moon where you're really in vacuum, but air has very little loss. So one of the new technologies, and some of you have heard this before, but photonic crystal fiber is one of the new things. Imagine a stack of capillary tubes from chemistry lab, those tiny little tubes that you might find in the little stock rooms. Stack them all up like that, heat it, and stretch it. And remarkably, the transverse dimensions maintain their integrity during the process, and you end up with a very tiny optical fiber that has a bunch of super tiny holes in it. And you can set things up so that the electromagnetic field maybe stays mainly in the middle one. So now my light is in air instead of in glass. So there's none of this Rayleigh scattering to give me this kind of loss as I go into the visible light and even all the way into the ultraviolet. even shorter wavelengths. So now I can take this, what pretty darn big, you'll see, this pretty darn big transmission window, suddenly whoosh, knock this all the way down to where I can have transmission all the way into the ultraviolet. I mean, this is, you're gonna need these things, trust me. There's no getting around it. This is the way in which you're gonna have that exponential growth in bandwidth continuing to happen. Right? You just can't keep laying more and more fiber in the ground. It's too expensive. So you use a better fiber that, wow, it's hugely better. So that would be an example of the next generation type of stuff. So I'll do a little mix of what's out there now, what's everybody talking about, and what can you expect to see coming down the pipeline. Questions, comments? I know this first part is kind of like me just talking a lot, too much. But later it'll be more like a conversation. So has anybody seen, or we saw a lot of people had seen that one, how about EDFAs? How many people have seen those letters, EDFAs? Cool. That's 100% more than I thought. No, that's infinitely more than 1 divided by 0 is infinity. Right? ROADM, yep. And passive optical networks. These are reconfigurable optical add-drop multiplexes. Telecom just has to have tons of acronyms, no getting around it. This stands for, how many people have heard of WDM, wavelength division multiplexing? Okay.
Yeah.
Put a D in front of it, stands for dense, Pac-Man denser. Right? Wavelength division multiplexing is also the same thing as the old-fashioned frequency division multiplexing. Right? Multiplexing has to do with how are you going to chop up all this bandwidth. We've got a certain amount of frequency and time over time. So how do I want to share things? If I chop things up in time, and maybe this is my entire frequency bandwidth of the radio or the fiber or whatever the system is, I chop things up this way, then that's time division multiplexing. Okay. And everybody has their own time slot. It's your turn, then it's her turn, then it's his turn, then it's his turn. Right. And then we go back around again. Another way of slicing it would be slice it this way. In green here, well, you can see that's green, frequency division multiplexing. That's like the radio in your car. One station has a certain band of frequencies, another has another band of frequencies. The telecom system, it started with the Bell system mainly, and Bell system used frequency division multiplexing. Everybody had a certain little channel bandwidth. Then it became more efficient to switch to time division multiplexing. The difference was how much are you wasting? The thickness of my pin mark here, I can't have one radio station right next to the other one. I need a little gap in between so they don't overlap. So I'm wasting the capacity there. Likewise, the thickness of my pin mark when I'm drawing the TDM lines. Well, I can't just switch from one person to another in an instant. It's going to take me a little time to switch from one to the other. So the technologies change over decade to decade, and so FDM was the best way to go initially, and then we got switches that ran really fast. And the Bell guys figured out, hey, let's go to TDM, it's going to be better, and it was. Then we go to optical, and they say, oh, we're back to frequency division multiplexing. That works better now. Nowadays, people are talking in the research labs, but it's not in the industry yet. Optical people going back to TDM using solitons. And I read a paper where it said, obviously, because there is an inherent advantage, TDM has an inherent advantage. It's just naturally naturally superior to FDM. we're going to see soliton systems installed. And I said, that better not have been one of my students who said that. There is no inherent advantage of one versus the other. It depends on the technology of the day, right? Can you switch faster, or can you pack in frequencies tighter? That's what drives the choice there. So you'll see those kinds of things happening. Right. And we have EDFA stand for erbium doped fiber amplifiers. And it's a neat little trick by which, and then I'll get on with it here. From a little dog and pony show here. How are you going to get across the ocean floor? The fiber has very low loss. At the minimum here, it's about 0.2 dB per kilometer, and I'll remind you or teach you if you never saw it before what a dB is. That's really very, very low loss. But how far is it from Beijing to San Francisco? It's a long way. That's a lot of kilometers. So if you're going to have these transoceanic fiber links, you still have too much loss. So you need amplifiers to boost the signal back up after a while. Well, an amplifier, I never saw an amplifier I didn't have to plug into the wall, right? My stereo, or batteries, right? Are you going to go out in the middle of the Pacific Ocean and change the batteries every month? Even if you paid me a lot of money, I still wouldn't want to do it. It costs too much. It'd be a nightmare. Can you have solar collectors on the surface and electrical wires through water? So there's a neat little trick by which you turn the fiber itself into an amplifier. So everything's made of atoms and such, right? And so if I have an electron and it's in its lowest, thank you. Please do that or throw something soft. Something is in its lowest energy state, right? Like we all like to trickle down to. Take a nap in our low energy state. But if I shine some light on it and I pump it up with one color, and then maybe there's a whole bunch of energy levels here that aren't spaced by so much, and their lifetimes are pretty short, so these are like little spin flips, and every time I lose this energy, it's just heat or something. But then it jumps down to here, and this gap is a different kind of a jump, maybe an atomic orbital jump. It doesn't happen as fast, so it hangs there. Well, now this energy difference is matched to my signal, so I have a pump, and then now I have a population inversion so that my signal can come in, all right, cleaner as we go. I'm just trying to cram it on the margin here. That can actually stimulate the emission of radiation, so it triggers this jump. So one came in, and there's the one that came in, the signal photon, but here, because that jumped energies, it lets go another one. So one came in, two came out, it's an amplifier. And what is it? It's a piece of glass that I shined a different color of light in. So rather than plug it in electrically, this amplifier is plugged in just by shining another color of light through it. And it pumps it up, turns the whole fiber into an amplifier. That's very simplified, of course, but shouldn't it be? And the people who came up with the stimulated emission of radiation is buried in that laser word, light amplification by stimulated emission of radiation. People who came up with the laser and the maser, they didn't sit down and solve a bunch of differential equations and all that. They sat on a park bench and they drew pictures like this. And they said, well, we ought to be able to do something like this, right? And then they went to or had somebody else go to the equations. And so if you don't understand it on a simple level, then you don't quite understand it yourself. That's my philosophy. So anyway, any questions about any of that? That'll give you a little feel for some of the topics that we're going to cover. These fiber amplifiers are all over the place. So you look at optical diagrams of a network, you'll see EFAs all over the place. There's a difference between an amplifier and a regenerator, as some of you know. And so the next greatest thing, the missing element for all optical networking would be all optical pulse regenerators. I've worked on it, many people have worked on it. They're not viable yet, but there's hope. So, again, I'll sneak in some of that, what's coming next stuff. Okay, on to course grading, but any other questions? Okay, something everybody cares about, right? Course grading. Here it is in a nutshell. Here it is spelled out. There will be 2 exams, and they're both 30%. And then there's a term paper, and it's also 30%. The term papers are easy. Everybody does about the same job of it. Yes, I read every single one of them. Yes, I grade every single one of them. The scores vary around a little bit, but not a whole lot, all right? So the term paper can wipe you out if you don't turn one in. You've thrown away a third. Don't do that, right? But don't panic on that being real difficult. We'll talk more and more about that. What's his homework? Only a measly 10%. So that means it's not so important? No. Homework is vital, because without the homework, you won't get those 2 big 30% items. Okay. So like it says here, although the homework comprises only 10% of the course grade, these are imperative, since they provide the problem-solving practice necessary for learning, hence doing well on the exams. Okay, so the homeworks are designed to prepare you for the exam, right? You do an honest attempt on the homework, and you look at the solutions and understand where you went wrong, then you should be golden on the exam. I get people who are getting consistently 70% on the homeworks, who get an A in the class because 10% of their 70 doesn't count as much, but they worked on it, they wrestled with it, they really tried. That's where the learning happens, right? Then they come into the exams, it's a piece of cake for them. How do you learn how to swim? Sorry, I'm telling some of my old jokes, but the new kids haven't. How do you learn how to swim? I mean, I can stand or sit here and say, this is how you swim. You wiggle your arms and legs around this way. Does that teach you how to swim? No. You learn how to swim when I throw you in the water and you splash around, you struggle. That's where you learn how to swim. That's what the homeworks are doing, right? Hopefully you'll come out of the lectures, you'll go, that was really clear. That was so simple. That was obvious. Oh, wow. Yeah. Hopefully. Well, you understood that, didn't you? Pump it up. Nothing to it. Hopefully you'll come out and you go, yeah, I understood that. I got that. And then you'll sit down to do the homework and you'll be, so, you know, you'll be going, curse that Shepard. Curse you, Red Baron. You didn't tell me how to do that, but I did. Right? But maybe you have to put 2 different pieces together to solve it. So that's where you're of course you're angry. You're splashing around the water, right? But that's good for you, okay? So you come out of it, you get a 70, but then you see the solutions and you go, oh, that's the part I was missing, right? Then you make sure you go over that. Then when a similar but different question comes up on the exam, you're all set. Okay? So that's the philosophy behind all that. Questions on that? Okay. 10 is monitored because I'm told I have to, but of course you have to travel. Lecture notes, as long as our equipment doesn't fail, also lecture videos will be posted either on Moodle or maybe somewhere else if that takes up too much memory. I will make makeup exams, but to be fair to the rest of the class, these have to be at least as difficult as the ordinary exam. So if I've got the flu, if I think I can still function okay, I'd probably choose to take the exam that everybody else is taking. Am I gonna punish you for having the flu? No. Am I gonna punish you for being in the hospital? Of course not, right? But I have to say it's going to be at least as difficult as the one that everybody else takes. But I'm okay with giving you a makeup exam. You should let me know in advance that what's going on and why you can't take the exam. I like doing the exams online in a kind of take-home sense, that you open it up on Moodle and you have 3 hours to finish it, but you have a week of opportunity to open it anytime you choose. I don't know why people worry about things, but some people worry about, oh, they're gonna cheat if you do that. You're not gonna cheat. You're professionals. Also, I can tell if you cheat. There's sneaky little ways that I get other kinds of information about statistics on what happened while you're taking an online exam. That I only saw one instance of it a long time ago. And but so I'd rather do that. But if people are saying no, that's not acceptable, then we'll have to have an in-class exam, which would mean everyone would have to be there on that day, or I have to email one out to Denver and one to Gardner or something at the same time. So I'll get back to you on that. The homeworks will be on Moodle. They'll be up there for a week, and there'll be 10 questions, multiple choice. The exams will be the same kind of format, 10 questions, multiple choice. On the homeworks, you can open it up, work on it, save your answers, go out to dinner, come back, work on it some more, go to sleep, come back 3 days later, work on it some more. And then as long as you click submit by the due date, then you're all set, right? And that seems to work pretty good. I used to be very old-fashioned, thinking that no, you can't have a multiple choice that does anything, and I need to see all your writing and get inside your head and figure out everything that you might possibly have been thinking about. But I've realized if I put up enough effort up front and really design in a well-worded, well-thought-out question, multiple choice does test your knowledge. And so, plus there's not enough math in this class for you. Oh, you flipped a sign there, you know. Oh, 2 times 1 is 3. No, that's too close. But there just aren't enough of those types of questions, so late homework cannot be accepted. Right, so make up exams, okay, but make up homework, no, we can't do that. You have a whole week, right? So, but if you're, you know, in the hospital for a week, you can't do it, that's fine. I mean, you can't do it, you can't do it. So what I would do instead is, instead of giving you a 0, I'd replace a 0 with your average on the rest of the homeworks. So if you can't do a homework, let me know why. And instead of getting a 0, you'll get the average that you got of the other homeworks. Questions about that? Okay. Textbooks and telecom, just, you know, by the time one gets printed, it's already out of date. So this is why you have someone like me teaching. I read all the time. I know I'm doing research, and I've read all the books. So lecture notes will be posted on Moodle, and that's really your best source. You can Wikipedia things, but Wikipedia sometimes gets it wrong. That's oftentimes Wikipedia, I find it pretty helpful. There are other online sources where you can go and you can Google Rotem, you know, you'll probably find a ton of articles, more than you want to ever look at in your life, no doubt. But there are 2 textbooks that I have listed here, and they're on reserve in the library on campus. You can probably get a hold of them. they probably have way too much math for anybody in the room except for maybe 3 people. But if you want to take a look at them, these are the ones I like. Carlson covers communication systems in general, and I like the earlier versions are better because it's shorter and it gets right to the point. The recent trends in textbooks is make it thicker, charge more, put in a bazillion different examples, but frankly I get lost. Right? I like something short, brief, right to the point. This one gets into optical communication systems, AgriLaw. We'll cover a lot of things. So that one might be a good thing to look at when you're thinking about your term paper. See what AgriLaw says. And if you want to see the nitty-gritties in more detail, that's a good source. Professionalism and ethics. Basically, don't cheat. You know that, of course. If you want to see all the nasty things we can do to you, if you do cheat, there's latech.edu/don't cheat for further details. I thought there was more to that link. But more seriously, you know, I would love you to discuss the course concepts during and outside of class, as well as, well, if you want to create online discussion boards. I don't think Moodle has any anymore. But don't discuss the homework answers before the due dates, because this only robs your friend of the learning experience needed to do well on exams. That also would hurt your standing, since all grades are relative to each other, according to a clustering procedure. Ethics and professionalism are very important throughout this industry also. Big, huge companies fall apart when their CEOs go off and try to do something sneaky. And so it's very important to be honest about what you're up to. But, you know, we all get busy, but if you're busy and you're like, I didn't have time to do 8, what did you get for 8? Don't ask that question in the first place, all right? It doesn't matter. It's a homework, right? The only point of the homework is to have you splash around and learn. You're not going to learn anything by putting down A, B, or C, right? You're only going to learn something if you look at it and go, I don't understand how to do number 8. Okay, maybe I'll go ahead and guess, but I'm going to jot down that I need to learn how to do 8 before the exam comes along, or I'm going to be in trouble. Okay. Also, the clustering procedure. Let's go over a little bit of that. I do kind of a scatter plot of everybody's scores and break them up into homeworks and exams and total scores. And in a class of this size, they always cluster up. It's really easy for me to see where are the A's, where are the B's. And there will always be a big gap, a reasonable, real gap between the lowest of the A's and the top of the B's. Okay. I won't name names, but I can't understand how somebody could say someone with a 90 gets an A, someone with a 89 gets a B. Come on. Why would you do that? Too lazy to look at your clusters? I will guarantee you that the clustering effect will only help you. If you've got above 90%, you know you're getting an A no matter what anybody else in the class does. Even if everybody gets an A, hey, that's great. That's fine. I love it. But this A-B line varies from class to class. But that's the way I do it. And I don't want to see any C's. So occasionally I do. It's usually when someone just, for some reason or another, doesn't put enough time into it, or they you know, if you don't turn in a term paper, ouch, oh gosh, fortunately no one's done that, but that would probably mathematically be a D or something. I gave an F once in my life. The person never showed up for class, never turned in a homework, never took an exam. I can't curve a 0, I'm sorry. Okay. No problems. The goals, like I said, I want you to understand the fundamentals. And I also want you to be able to assess the future potentials. Right? And then this is, I don't know why they want all of us to say this. We're going to evaluate this in a specific way for our evaluation. And I think evaluation's good. It's good to evaluate, you know, is my teaching really working or am I deceiving myself? So I do care about evaluation, but why should you? I don't know why this has to go on the syllabus, frankly, but it's okay. I look at percentages of students who satisfactorily answer exam and homework questions specifically targeted at these particular goals. So I set up, okay, question number 3 on homework 2, that's fundamental, I'm going to use that one, see how people did on that to assess the performance. Sorry, I'm talking about something I said I don't know why it's there. I'm just taking a nap. All right. It's understood you have to travel, right? I keep permanent records because I'm told to. If I see excessive absences without any reason, then I'll track you down by email and say, hey, I'm still in class, what's going on? If anybody has any type of disability at all, please let me know. We have Office of Disability Services, and there's the right website that can help you with that. I myself think that I'm kind of slow, and slow can be a good thing, but likewise on the exams, I don't try to test how quickly you can use your calculator. Hopefully there won't be any numbers at all on it, but speed should not be a problem on the exam. I'd make it so you have 3 times as much time as you would need to do the exam, and still check all your answers. And that's, you know, about 20 times as much time as it takes me to do the exam, and I'm slow. But of course I wrote the questions, so that's cheating. Okay, there's an honor code at that website, and you pledge allegiance to the honor code. And I don't think I have to, I guess I have to have that there, but I don't have to hear you say it. You're all honorable people. There's also an emergency notification system. You think it's going to snow this fall? I don't know. Weather's been pretty crazy. I do like the idea of not driving in snow, especially in the south. I consider myself to be a southerner now. The snow bothers me. I was a student in Boston for grad school. I grew up in Kansas and went there for undergrad. But so of course in Boston they never closed anything for snow. And so one day I'm walking home from class to go back to the dorm, and I'm walking along and I look down and suddenly I realize I'm standing on top of a car. There's a frickin' car underneath me. And of course they plow the streets, and then that piles it up, and then it drifts. So it wasn't like it had snowed that high to bury a car on its own, but still, that was a lot of snow. And I tell people in the South that, because here, I mean, one flake. I don't want you on the road. Remember what happened in Atlanta? They let everybody go at the same time. I was teaching a class then, and I said, look, we're not having class. I don't think they had officially closed, but I said, I don't want you people on the road. And it was a good thing, because in Atlanta they waited too long, and then they let everybody go at once, and they stuck in traffic for, was it days or what? Anyway, any questions about anything? All right, let's get into it then. I won't always do pre-lecture notes, but sometimes I will. Usually I'll only do it when there's a whole lot of words, but I wanted you to kind of get used to the concept. And so this is an equation that you saw in high school. Frequency times wavelength equals velocity, right? But I put a little subscript here on velocity and called it phase velocity. Actually, this is the velocity that's useful for knowing what Snell's law, why a straw looks bent in a glass, and how fiber works and things like that. But this is actually the velocity you don't really care about in telecom. This is not the speed at which bits fly along. This is the, we'll see later, this is the speed at which the zero crossings of the field propagate, but it's not the speed at which the pulse propagates. Pulse propagates at something called a group velocity. We'll get there when we get into dispersion. But this is the one you know from high school. Frequency times wavelength equals velocity. It's actually the velocity that's not as important as the one you'll see later. This can be written as c divided by n. C here is Einstein's speed limit. It's the speed of light in empty space. It's real darn close to exactly 3 times 10 to the 8 meters per second. All right. And n here is the so-called index of refraction. So index of refraction. I would argue that phase velocity even can't go faster than the speed of light. So in that sense, index of refraction then needs to be a number bigger than, greater, that stands for greater than or equal to 1. Right? So if I'm dividing by a number that's bigger than 1, I'm making that whole thing smaller, right? If I plugged in 2, it'd be half of Einstein's speed limit. Okay. Make sense? Cool. There's another thing that's useful, kind of a change of variables here in optics. Rather than talking about the wavelength, it's more useful to talk about the wave number, which is k. Equal sign with 3 bars means equal to by definition, if you like to use that. So k, by definition, is just 2 pi divided by wavelength. And likewise, frequency is more friendly if you stick up 2 pi here also, and we call that omega. So instead of f and lambda, it's usually k and omega. Right. So if I take this frequency times wavelength equals velocity, rewrite it in terms of my new friends, k and omega. I don't like algebra. I spent most of my algebra classes in principal's office for talking to all the girls next to me. But quantum algebra I like. But regular algebra, I cringe. So bear with me here. K would be 2 pi divided by lambda. Omega 2 pi times f, so I have 2 pi f c. I would go to where no one can look at me, and I'd sit down and work that out on a piece of scratch paper, and then I could quickly say, oh, okay, that's saying the same thing. Right? You want to see me do it? I'll do it. We're all friends. You won't make me nervous, right? You won't make fun of me if I goof it up, right? K is 2 pi over lambda. Is that really the same thing as omega divided by times n? Well, omega's 2 pi times frequency. Is there a c? Did somebody shout out a c? Yeah, thanks. Omega divided by c. Yeah, that's right. So that's 2 pi. C divided by n is velocity. And so saying that that is equal to that says the same thing as, it's been a long day. Started at 4 a.m. 2 pi over lambda equals 2 pi f divided by v. Sure, because I can move the lambda over there, the 2 pi's cancel, and the v went over there.
Show your work.
Oh. I lost 10 points for not showing my work. Okay, so I put in 2 pi over lambda, I put in 2 pi f, I started to write divide by v, and instead I threw the v over there, and then I canceled out the 2 pi's, and I took the lambda and shoved it over here. And sure enough, it just says v equals frequency times wavelength, which I knew in high school. We all knew that in high school. So this is another way of saying frequency times wavelength equals velocity. It's in terms of our new friends. You'll see why that's helpful later. Actually, yeah, I'm going to do that this way. A lot of times I'll do an aside, and I'll label it an aside. An aside means you can take a nap now if you like. And then when I say end of aside, you need to wake back up. Right? Asides aren't totally worthless, but they're asides, right? So if it's bothering you, if an aside bothers you, skip it, right? Maybe extra info. If it helps, wonderful. If it doesn't, hey, it's an aside. But you can ask questions within an aside. So questions about that? Why am I so bad at arithmetic? I already told you. Algebra. Okay. Snell's law. How many people remember hearing Snell's law? Really? Okay. How many people have looked at a straw in a glass of water and it looks like it's bent? Okay, so that's Snell's law. Good, then you haven't seen this N1 sine theta 1 equals N2 sine theta 2. It's really boring, and the only problem people can think of is give you 3 of those things and ask you to solve for the 4th. Here's a better way of doing Snell's law. It's graphical. Then you can see things. K sub x is continuous. What does that mean? Well, this is what that means. We've got an interface between 2 media. This one has an index N1, this one has an index N2. Let's call this direction the x direction. And we said K is omega divided by C times N. K is now going to be a vector, right? And it can only be so big. This is the length that K can be. It can be as big as omega, well, its length is omega divided by C times N. What's N? I'm in index 1 here, so K can be that big. I can launch a wave in the direction of this K vector. Call it K sub 1 because I'm in medium 1. I'll put a bar over it to indicate vector. This is probably way more math than we'll do the rest of the class. This, you're all set. It's not that much. Just don't get scared. Take it piece by piece. This also illustrates that you really need to look at the lecture videos. When you see this unfolding step by step, it's not so bad. If you just look at a lecture note, scary, right? That scares even me, okay? So, yes, look at the lecture notes, but make sure you've seen the lecture video, because just trying to get it straight from the notes, you're challenging yourself way harder than you need to. So I'm coming in at some angle. Let's call that theta 1. theta 1 equals 0, I'm launching that wave straight onto this interface. Maybe this is air with index N1. Maybe this is a piece of glass with index N2. I'm shining light from this medium into this medium. Some of it's going to reflect, some of it's going to go through, right? We're leading up to how optical fiber works. So, come in at that angle, and then down here I have some other index. Let's say it's such that this k vector can be this big, omega divided by c times n2. So I've drawn that radius of that circle smaller, so I'm drawing this for n2 is smaller than n1. Okay. So can N1 be air and N2 be glass? No, glass is denser, so it has a bigger index. That's the way to think of that. Air is close to vacuum, so the index is as small as it can be. It's real close to 1, right? So if this is the smaller index, then maybe I'm launching away from the glass into the air. Then this would be appropriate. This one's denser medium than this one. Okay. So maybe I'm inside the fiber, trying to go outside the fiber into the air. Fiber's made of glass. It's a bigger index. Okay? Questions on that? Okay. So what the heck do I mean by k sub x is continuous? This is k sub x. This much. It's the x component of this k vector. So on this side, the x component was this big. With me? Cool. So on the other side of the interface, it has to be that same size. So I measure this, and I plunk it down over here, and it's that much. So